The vanadium redox cell, or the vanadium redox flow battery, was invented by Maria Skylas-Kazakos and her research team in 1985 in the University of New South Wales. The idea of creating a vanadium redox battery initiated based on Maria co-supervising a student doing a research task on the redox flow battery from NASA. As they continued to research, they found many problems with the redox cell, such as the membrane not being able to permanently separate the two solutions, which therefore led to the mixed solutions constantly having to be replaced. Therefore, the idea of using an element with different oxidation states emerged in comparison to a normal flow battery, which has two different solutions. Since there had been no recollection of work done of vanadium in a redox cell, Maria had an assistant, Elaine Sum, who was an honours student, to help her with her research. They discovered that the electrode will work if it was scraped and roughed for it to be activated in order for a reaction to occur. Further problems arose, such as the solubility of the 5+ ions, as well as the level of concentration of the sulfuric acid. The structure of the vanadium redox cell includes two external tanks, where the energy is stored and travels through pumps which are attached to the main battery or the cell stacks, this being where the energy is converted. As there are two separate reactions occurring, a membrane splits the cells in half, one half containing a negative electrode and the other half containing a positive electrode. This is where the oxidation and reduction occurs. The vanadium redox cell is a flow battery in which stores electrolytes in two separate external tanks through the use of one element, vanadium, in different oxidation states, V2+, V3+, V4+, and V5+, all containing sulfuric acid. The tanks are distinguished as an anode and a cathode, containing two different oxidation states of vanadium. The anode is where the oxidation reaction occurs, whilst in the cathode the reduction reaction occurs. Both the catholytes and the analytes are pumped into the battery stacks in half cells, where the oxidation-reduction reaction occurs. When the process is undergoing the discharge cycle, meaning it is releasing energy to an external source, within the anode, the oxidation reaction takes place. The V2+ loses an electron to become V3+. The ions react with the negative electrode and all the hydrogen ions diffuse into the other half cell. The incorporation of the sulfuric acid within the electrolytes allows neutrality, where the hydrogen ions from the acid diffuses to the other half cell, forming water, but the hydrogen ions and the water are to maintain the charge of the reaction. At the same time, within the cathode half cell, a reduction reaction occurs. The V5+ gains an electron, becoming V4+, as the ions react with the positive electrode. From this redox reaction, the chemical energy is converted into electrical energy, emitted through the battery for the external source. In order for the battery to charge, the process is reversed, where it is connected to an external power source. The charge reaction is opposite to the discharge reaction, where the oxidation and reduction equations change, hence the following equations. The vanadium redox cell is used as storage for wind and solar energy, electric cars, energy storage systems such as load leveling, and in the future, the potential to be used in residential homes. The battery can offer almost unlimited energy, as the tanks can be replaced with a range of sizes. The larger the tank, the more energy it can charge or discharge. Since there are a larger number of vanadium ions of different oxidation states in each tank, the oxidation and reduction reaction occurs on a large scale, therefore charging and discharging large amounts of energy. The vanadium redox cell is used to provide charging stations for electric vehicles. There will be a simultaneous discharge and charge of the electrolytes, allowing vehicles to be connected to the power station. The vanadium electrolytes undergo the oxidation and reduction reaction, where the chemical energy turns into electrical energy. The electrical energy then flows into the power load, where it is connected to the external source, the electric vehicle, and is pumped into the car. The vanadium redox cell is not a largely implemented piece of technology, and is also fairly new. Hence, the impact on society and the impact on the environment is not significant in the present day. The production of the material is beneficial, as vanadium ions are used in the process instead of other elements that are more dangerous in terms of being flammable and hazardous. Vanadium is said in the future to replace lead-acid batteries in some applications such as electric cars or storage systems. This is beneficial as vanadium is not flammable and non-toxic, in comparison to the lead-acid battery, which is highly flammable and is hazardous. This is therefore being a safer option for people, especially when it is used in their homes. Due to the emergence of this technology, electric cars have become a new form of transportation that is having a high potential for the future. It is more easy and more practical, and it lasts longer, resulting to time efficiency for highly scheduled workers. However, a negative impact of the production of the vanadium redox cell is its current expenses, especially for the cost of the membrane, which is 40% of the total cost of the cell. If the cost is high, people will continue to use lead-acid batteries, which negatively impacts both society and the environment. The production of the material is environmentally friendly compared to other batteries. Since the analytes and the catalytes are all the same element, replacing them does not impact the environment. They do not need to be disposed since the electrolytes can be recycled and reused. The vanadium is simply replaced once used up. They are also not dependent on fossil fuels, therefore minimizing the risk of air pollution, hence beneficial for the environment. As mentioned before in comparison to lead, vanadium is less toxic and less flammable, as in the lead-acid batteries. There is more of a risk of the battery being overloaded and filled with explosive hydrogen gas. Hence, if the vanadium redox cell replaces the lead-acid cell, there will be more of a positive environmental impact, as there is less of a risk of the cell becoming flammable, harming the surrounding environment, as well as the tendency of the spillage of any harmful chemicals. Also, the increase of the vanadium cells in electric cars and power stations lessens the air pollution in the environment, as the use of petrol or diesel is minimized, meaning there will be less inhalation of toxic fumes and gas affecting the respiratory system in large populations. Instead, simply, the electrolytes are replaced where there are no deposits that will affect the environment. Overall, the vanadium redox cell has a positive impact on both society and the environment from its production and from its uses.